Okay. Today we will consider half-range expansion of the function defined on a finite interval. Suppose the finite interval is from 0 to L. So just like that. Okay. All right, and our purpose is we want to represent f of x as a Fourier series How can we do so? Well, we can do it by extending f of x into a periodic function. Okay, so we can extend it because this function is defined only on a finite interval from 0 to L, right? So, but as we discussed from our previous section, that we can expand a periodic function by using a Fourier series. All right. Now, if we do so by regarding f of x, x is in the L as in a period of a periodic function. Period L E Okay, so if we regard the original function f of x as in a period of a periodic function, so this is f a x is a periodic function with this period L here, right? So this is like that. Then the Fourier series extension, okay, f of x would have a0, a1, b1, a2, b2, etc. as coefficients. Okay, so you will have a cosine term and sine term. Okay? So in general, you will have such terms. right? So n contains both cosine and sine terms. Right? So this is one way. Okay. But we can simplify representation. But we can simplify the Fourier series extension by using one even periodic extension set of one okay, so this is even periodic extension. How can we construct such a right? So this is the even okay. So f1x. So f1x is an even periodic extension of f of x. So where f1x is an even periodic function of period 2L. Okay? So now f1x has a period 2 times L. Alright, compared with this periodic function. For fa, this is a periodic function with period L. It's L. Okay, and then how do we construct that? Well, f1 x is defined to be f of x when x is in between here and L, and f of minus x if it's in between minus L and 0, and the f1x plus 2L is equal to f1x. Okay, so f1x is defined this way. Okay, so this implies that f1x minus x is equal to f1x. So by this definition, f1x is even. It's an even periodic function. Okay. And we know for an even periodic function, The Fourier series expansion consists of only cosine terms. Okay? So f of x, so that f1 x is equal to a0 plus summation an cosine pi x. Okay? For all all. Okay, and a0. So thus, for x in 0 and L, f of x is equal to f1 of x. Because the original function f of x is equal to f1 of x in this interval from 0 to L. Okay, so f of x is equal to a0 an cosine pi x divided by L. Okay, and where a0 is equal to 1 over 2L, or we know that because it's even function, so this is 1 over L. Okay, and the an is equal to okay, and this is equal to okay. So this is called this is called the even half range of extension of f of x. Now you understand the reason why we call it half range, because that's the original function f of x is just a half range of the even periodic function. Yeah, because the period of f1 of x is 2L. Any questions? All right. Now, we have a second simplified representation. So we will consider the second alternative. Odd periodic extension f to x of f of x. Yeah. So you see that f sub 2x is a periodic function with period 2 times L. Okay. So where f2 of x is an odd periodic function. Okay, of period 2 times L, and the definition of f2x is f of x when x is in 0 and L, and then minus f minus x and the f2x plus 2L equal to f2x. Okay. Okay. So we define f2x to be like this one. Okay. So we have so f2 of x is an odd function. Okay, so f2 of x becomes the summation bn sine n pi x divided by L. Okay, for all x in R. Okay. So because f2x is a periodic function, okay, on the real line, and thus for x in 0 to L, the original function is equal to f of x, so this is become true. Okay? Where Pn is equal to so this is called the odd half-range extension. Of f of x. Okay. All right. So the last two representations, the even and odd half-range extensions are commonly used to represent a function defined on finite intervals from 0 to L. So you can see that the same function can have two different representations. Any questions? Okay, so if there is no further question, I will go to discuss a very important topic called the Sturm-Liouville problem. Now, the success of Fourier series extension of a periodic function is due to the orthogonality property of the trigonometric system. Okay, we have observed this ray, right? So let me state the orthogonality property of the trigonometric system again. So actually, this is because that 1 times cosine mx dx equal to 0. Minus pi 1 times sine. Okay. By using the inner product space of L2 space, we know that this is just 1 cosine mx 1 equal to 0. Okay, so inner product. So the inner product of the constant function and the cosine functions are 0. Okay, so they are both 0. Okay. In the vector space. Okay, as we defined last night. Okay. So here and A, you know that the second one says that cosine mx is 0. Okay. E from the sine function. Okay, so this is the basic property we used when we discussed the Fourier series extension. Now in this section, okay, so we will discover many other systems. Okay, of orthogonal function developed from the Sturm-Liouville problem. And generalized from generalized the idea of Fourier series. Generalize the idea of Fourier series and extension. Okay. So the point is that Fourier series extension is just one of many orthogonal extensions you can have. So trigonometric system, just one of many orthogonal system of functions. Okay? So this is the idea. And this idea is fundamentally important in physical science. So I'll try myself to introduce the concept as clearly as possible. And but if you get any questions, just please raise your hands and ask the question. Okay? All right. So consider a second order homogeneous linear ODE of the form. Okay. So it's P of X, Y prime, and prime plus Q of X plus lambda R of X Y is 0. And this is okay, this differential equation is called Sturm-Liouville equation. Okay. All right, and on some interval, okay, say AB, and satisfying the boundary condition. Okay, so satisfying the boundary condition at the two boundary points A and B. So A, let's say 1, K1, Y, A plus K2, Y prime A equal to 0. The second one is L1, YB plus L2, Y prime B equal to 0. Okay, so we have two boundary conditions. The first one govern the boundary condition at the endpoint A. So K1, K1, K2, L1, L2 here. Lambda here, is a parameter. Okay. And K1, K2, L1, L2 are given constants. And at least, okay, and at least one of the two constants in each condition in 11.5.2 must be different from 0. Okay, so in this condition, at least one of K1 and K2 is non-zero. And in the second condition, at least one of L1, L2 is non-zero. Okay? So this one must be different from 0. Okay, so the ODE in 11.5.1 together with the two boundary conditions in 11.5.2 is called the term behavior problem. Okay, and stem behavior problem is an example of boundary value problem. There are, of course, there are many boundary value problems. And the Sturm Liouville problem is one of the important problems. Now, first of all, you can see that the Sturm Liouville problem has a trivial solution. Because the ODE is homogeneous in linear. Why? Okay? Right? So the solution is identical to 0. Right? This is, of course, there is one solution. But we are interested in non-trivial solutions. And we'll give names for those non-trivial solutions. So any non-zero or non-trivial, let's say, non-trivial solution of the Sturm Liouville problem is called an eigenfunction of the SL problem. And the corresponding parameter lambda for such an eigenfunction to exist okay, is called an eigenvalue of the Sturm-Liouville problem. Okay, so you see that if we have a non-trivial solution for this ODE satisfying these two boundary conditions, then any such function is called an eigenfunction. And the corresponding prime number for such an eigenfunction to exist is called an eigenvalue. Okay? Called an eigenvalue. Alright, so let's take an example. Alright. Actually, trigonometric functions are eigenfunctions. Okay, of certain Sturm-Liouville problem. All right. So first of all, consider a very simple. All right, very simple homogeneous linear ODE. See here, very simple, all right? And the boundary condition is 0, okay, and 0. Okay, so we have two boundary conditions. One at the endpoint 0, the other endpoint is pi. So y is 0, y pi is 0. Okay. Okay, and this problem for 11.5.3. Okay. All right. So now compare with so this is the general Sturm-Liouville problem. This is a specific Sturm-Liouville problem. So we can see that P is a constant function. Q is equal to 0. R is a constant 1. A, the left endpoint is 0. The right endpoint is pi. Okay? And we know K1 is equal to 1. K2 equal to 0, L1 is equal to 1, but L2 is equal to 0. Okay, so this is all the information we need to form a Sturm-Liouville problem. Okay, so you can see that this is all the data we have. Okay, so now we try to solve this problem to find whether we have non-trivial solution. Okay? Okay, now, if lambda is negative, right, and any negative number can be represented as minus mu squared, right? Any negative number. So then, a general solution, okay, of 11.5.3, okay, it's 1 over x equal to C1 mu x plus C2 x, okay? Right, so we have two, then y is 0. So we put into the boundary condition. Okay? So boundary condition y is 0. So when we put y 0 here, we have c1 plus c2 equal to 0. And y pi, okay, y pi is c1 e pi mu plus c2 e minus pi mu equal to 0. Alright, now we have two equations to solve these two c1 and c2. Okay, so we have 1. Okay, but this matrix is non-singular because its determinant is non-zero, right? So non-singular. So this implies that C1 is equal to 0. So we have only trivial solution. So if lambda is negative, we have only trivial solution. Okay, so we have only trivial solution in this case. The second thing is, if lambda equals to 0, then the general solution of this problem is C1 plus C2x. Okay? So if this is 0, then we have the second derivative of y equal to 0. So y should be a linear polynomial. Okay, this one. Okay, and so then y is 0, and y pi So C1 is 0 and C2 is 0 too. So we have, again, we have only trivial solution. Again. Okay. So the last, so for lambda is equal to mu square. So if lambda is positive, okay, the general solution A cosine lambda x plus B sine lambda x. Okay? Oh, mu, I'm sorry. Because lambda is equal to mu squared. So mu x plus B sine mu x. Right, so we have general solutions. And then the two boundary conditions. Okay. Okay, because this is 0. So A is 0 and the y pi is B sine mu pi equal to 0. Okay. Alright, so the first boundary condition dictates that A should be 0. right? Because when you put 0 here, it vanishes, right? So, and this is 1. So you have A, but A is equal to 0 from the first boundary condition. The second boundary condition tells us that because A is 0, right? So we have only this term. So B times sine nu pi is equal to 0. So this is the only hope we have non-trivial solution. So we will have a non-trivial solution. I.e. B not equal to 0. Right? Because if B is 0, then the only solution is trivial. Then we have no solution, no non-trivial solution, right? So to have a non-trivial solution means that B cannot be 0 because A already must be 0. Alright? So the only thing is to have a non-trivial solution means B not equal to 0. We must have what? The sine nu pi equal to 0. Okay? So this is the only hope. And the only condition is that when nu is an integer. Right? So this is the only hope. Nu is an integer. Okay? Okay, so since nu greater than 0, right? Because here we assume nu is than 0, that we have lambda is n squared. Okay, and the corresponding we have eigenvalues. Alright, so eigenvalues are n squared. So it's 1 and 4 and 9 and 16, etc. Right? So n squared. And the corresponding eigenfunctions are sine nx. Okay? So you see sine nx is now. They are eigenfunctions. Okay? And sine nx are members of our trigonometric system. Okay? Right. So I stop here for the first.